Better now? Ooh. Okay, maybe I'll whisper. Okay, so like I said, I'm talking about a project I've worked on with a whole bunch of collaborators within Utah, trying to identify how urban impacts are getting into our rivers. So start with some really broad background of why all this matters. All over the world, urban populations are increasing. We're seeing this in North America. We're up to about 80% of our population is living in urban centers, and we're seeing this in a lot of other places in the world also. And these growing urban populations put increasing stresses on our natural resources. These populations themselves have increasing demands on these resources, but also as our urban centers grow physically, they also alter the landscape, which put additional stresses onto our natural resources. So we want to identify how how this growth in urban systems are interacting with these natural resources, how we can better protect them as we grow our cities. Additionally, throughout all of human history, we grow our cities, we grow our population centers along waterways. These waterways provide drinking water, they provide places to put our wastewater and carry our waste away from our cities. They provide a lot of other services in addition to those direct sources of water services. So they act as transportation for people and goods moving in and out of the cities. We use them for recreation, for kayaking, for fishing, for just going down and playing in the water. So there's a wide range of services that these waterways provide. Unfortunately, all of the impacts of urbanization can affect these services we get from our rivers. So cities we build, when we build them up around our rivers, they alter our rivers physically, chemically, and biologically. We channelize our rivers. We take these natural meanders and curves and we make them straight, and we line them with concrete, which interferes with the connectivity of the water in the landscape with the water in the river. We also will get rid of a lot of the headwaters. We'll pipe them, turn them into underground pipes, and remove the connectivity that way. And we also put down concrete and make impervious surfaces, which can prevent and sort of control how water is going into the ground, which then feeds into the river. And that can also lead to flash floods and different responses to large precipitation events. So all these different physical changes affect the hydrology of how the water is moving through the watershed. Additionally, we alter things chemically. We put a lot of road salt down in the winter, and then that salt, a lot of it ends up in the river, changes the connectivity, changes the water quality in the system. We have nutrients that enter our river through fertilizers, through wastewater treatment plants, all these other sources that also alter the chemistry, both in terms of conservative and nutrient sources. All of these combine to then have biological effects on the rivers. We may put non-native species either in the water itself or as plants along the side of the rivers. The different changes in the physical and chemical properties of the river end up with ecological degradation. We may have so much chloride that certain plants or fish can no longer survive in that area. So with these changes of these physical, chemical, and biological changes all then affect how we can use these rivers and what services they can provide for us. When we think about urban water management and how these effects are happening and what we can do to try to mitigate them, we tend to have a model that focuses on surface runoff. So we picture rain falling and hitting a roof, running down the side of a building, hitting a street, running into a gutter, and then going into the stream. And we tend to picture that most of the impacts coming from the urban system are coming in through these pipes. So a lot of management is focused on how can we treat what's going into these pipes, what's going out of these pipes. Can we make bioswales or other things that will help absorb some of those nutrients? And if we can just focus on these small parts of the system, maybe we can have better water quality within our rivers. But we know in natural systems, in watersheds, we have a lot of interaction between subsurface water and surface water. And so we could very well be seeing that in the urban system too. And if we ignore that part of the puzzle, then we're not going to effectively treat and mitigate all these water quality impacts. So we focused in on the Wasatch Front, and we wanted to know what are these flow path controls on urban impacts to water quality. We see water in our streets, we see all these pipes flowing into our streams, we see these channelization impacts, but how are these urban impacts actually getting into our streams? We started with Red Butte Creek. Red Butte Creek is a really nice natural experiment for this. We have about 6 kilometers of the creek located in the canyon, which is a protected area. So there's very little human impact to the stream in this upper section. And then Red Butte Creek flows into the university. It flows into a neighborhood that's been around for about 100 years. So it's this well-urbanized, long-term urbanized landscape. And so we have this natural experiment of a stream that starts in an unimpacted area and then immediately flows into an urban system, and we can compare these two sections of the creek. So we worked with a large group of scientists to perform several synoptic surveys. We sampled during snowmelt, during the winter when snow was on the ground, in the summer when flow was low, to make sure we could see what was happening in different flow conditions. We measured a huge range of variables. We looked at the hydrology, so the actual rate of flow, how much the water was flowing. We looked at the chemistry of the stream, conservative solutes like chloride, nutrients like nitrogen. We looked at the soil next to the stream to see if there's changes in the soil conditions itself in the canyon versus the urban system. We looked at the riparian vegetation, how is that changing in the canyon versus in the city. We also looked at microbial population and macroinvertebrates. Just giving you an idea of this giant suite of data that exists and is being worked on. I'm not going to talk about all these variables today. My work is focused mainly on the chemistry and the hydrology, but all these other studies are also coming out, getting published. Some of the data is available. So for Red Butte Creek, we sampled at each one of these red dots. So about 6 kilometers up in the canyon, about 6 kilometers in the urban system, ending just before the stream goes underground and is then pumped into Liberty Lake. Some of these sites we sampled at every one of our sampling events. Some of them we couldn't, either because of personnel restraints or because some parts we can't access when there's snow on the ground. But we did our best. So first I want to focus on what we're seeing in some storm areas. So this is the sort of end of the university. So we have an area where Utah has instrumentation measuring discharge or flow. And our upstream location is just downstream of Red Butte Gardens, and our downstream location is just upstream of Foothills. So it's about not quite 2 kilometers distance between these two locations along the stream. And in that section, at each of these locations, we have discharge being measured continuously. And then we have 4 different storm drains where we also have discharge measured continually. We have the biggest storm drains that are present in this location measured. There are other storm drains and other spots where water can pour into the stream during a storm, but we're measuring most of the water that's entering the stream. And if we look at a sample storm event, we see in this top graph precipitation, so this is the rainfall that we're measuring. And then in this next one down, we're seeing that discharge from those in situ sensors being measured during the storm event. So the black line is the upstream, how much water we're seeing in that upstream site. And the black line is pretty much flat all the way through the storm event. So until we hit campus, we actually don't see a huge response in Red Butte Creek in the flow during a rain event. The red line is this flow down here, so that downstream. And then the blue line is the sum of the flow from these storm drains. Remember, this isn't all the water coming into Red Butte Creek during a storm event, but it is probably most of it. What we see here is that storm drain sun is higher than the discharge that we have downstream. If we look at the total sum, the red is the sum of what we're seeing at Foothill Drive, and the black is the sum of what we're seeing upstream plus these storm drains. And that black is a lot higher than that red, which is telling us that water that's coming in from upstream, that's coming in from the storm drains, is almost immediately recharging into the subsurface after it hits the stream. So just in that short distance, we're seeing all this storm water that's carrying all these urban impacts, these high chloride, these high nitrates during a storm, going right into the subsurface. So we have evidence just from these storm events that we do have urban impacts recharging underground. So I want to see if we can see that then impacting the stream further downstream. So this is some of the data from these synoptic surveys. So we have a longitudinal, going longitudinally from the headwaters in the canyon all the way down until Red Butte Creek goes underground just after 1100 east. So the first 6 kilometers are the canyon. And when we look at the discharge, so how much water is flowing through the stream, what we see is that in the canyon we're seeing a slowly gaining stream. We're seeing a very slow, steady increase of discharge as we go down the canyon. And what we're seeing is we're seeing groundwater entering the stream and increasing that discharge as we go downstream. We're also seeing not a lot of variability across the season. So we see a little bit more flow during snowmelt, but in general it's just sort of a slow, steady gaining system, one source, not a whole lot of variability. Then when we enter these first 3 kilometers of the urban system, so this is from when Red Butte leaves the canyon until it reaches Foothill Drive, in this section we're seeing much greater variability. We're seeing a huge difference in the discharge rates between the different seasons compared to what we're seeing in the canyon. So we're seeing this sort of effect of this urban system of this huge range in discharge, but we're seeing overall it's slightly losing. So if we look at any individual sampling event, we're seeing a very slight decrease in discharge as we go through this section. So it's that indication of that water is recharging into the subsurface in this area. And then when we go below Foothill Drive until where Butte Creek goes underground, we're starting to see a gaining system again. We're seeing water coming back into the stream. We're seeing a lot less variability. So it's back to sort of one source, not a huge range of differences in how much water is in the system. We then compare the hydrology, so how much water there is, to the isotopes. And the isotopes are a measure of the water itself. So water can have oxygen that weighs 16 or oxygen that weighs 18. And by looking at the ratio of those two different weights, we can see what water is present in the system. And so water that's exposed to different amounts of evaporation will have a different ratio of those isotopic weights. And if we see that rate changing, we can say either that water is exposed to different evaporative effects, and so it could mean that we have different sources of water coming in and mixing in a different location. So in this canyon, where we're seeing this slowly gaining system from the hydrology, we're just seeing a slow, steady increase in the O18, which is that fraction of 16 to 18 weight in the oxygen molecule, or oxygen atom in the water molecule. And so in that case, we're seeing this is probably just an evaporative effect. As this water is moving downstream, it's just very slowly evaporating. We then see a big jump after the reservoir, which is a signal of evaporation from the reservoir. But we've also got a wide variability again in the oxygen isotopes. In that same section, we see the variability in the discharge. And so this is telling us we're seeing either highly variable source or variable mixing of different sources happening in this section. Where the upper section, we've got one source coming in. Here we have variable sources. Then when we go to that lower section where it was gaining and less variability in the discharge, we also see a decreasing variability in these isotopes. We're seeing that variability gets smaller and smaller as we go downstream, which is telling us, okay, we're again having this one single source, where upstream in that urban section it was a mixture of sources. We then add in the chemistry. Chloride is a really common indicator of urban impacts, mostly because of road salt. Chloride is very low in the canyon, doesn't really change a whole lot. We start to see a slight increase in this upper urban section through campus. Even though there's a big giant pile of road salt that sits next to the stream in the winter, we're still not seeing a huge increase in the winter in spite of that. And in spite of these highly variable sources, we're still not seeing this indication of a lot of urban impact. And yet, when we get to this bottom section, we're seeing chloride exponentially increase, going from 20 milligrams per liter to 150 milligrams per liter. So this single source that seems to be coming in this section based on the discharge and the oxygen isotopes appears to be an urban impacted source. So hydrology is telling us that in that lower urban section, we have this new stable urban impacted water source. We also see that in the biogeochemistry. So we looked at the dissolved organic carbon and the nitrate concentrations. And in the canyon, dissolved organic carbon concentrations are low. Expect to see that in a cold groundwater fed stream. It's not surprising. Upper urban, it starts to increase a little bit. That could be impacts from the reservoir. It could be impacts that the fact it's a losing stream. It's water that's staying in the surface longer and building up more carbon. But then in the lower urban section, we see that carbon decrease again. In the nitrate, we see very low nitrate values in the canyon, very low nitrate values in the upper urban section in spite of all the storm drain input, in spite of that variable mixing sources. And then we see nitrate concentrations go 4 or 5 times that amount in the lower urban section. We see this sudden increase in nitrate. What we did was we found that in that section there were a lot of groundwater springs that we could see going into the stream, so we were able to measure those. So these are springs from the groundwater feeding into the stream. And these springs have really low organic carbon. So maybe this lower urban has the carbon going down because these springs are coming in. This new source of water is these springs, which is bringing in low carbon water. These springs have really high nitrate values, so that explains why we're seeing this increased nitrate in this lower urban section. We're seeing these groundwater-fed springs that are high in nitrate feeding into this section, increasing the nitrate in this section. So we have this alluvial aquifer, this subsurface aquifer that's pretty close to the surface, that's feeding back into the stream that has urban impacts. And there's 2 possible sources of water to feed into that alluvial aquifer, which is then feeding those springs. We have mountain block and mountain front recharge, so water coming from the larger regional watershed from the canyon that's coming in from the mountains and feeding into the groundwater. And then we have urban runoff from the local watershed, so whenever it rains we have it coming from the parking lots and the roofs and the streets, and it's picking up all these chemistry from this urban system and feeding into the alluvial aquifer that way. And I'm having a Mac to PC problem with this figure, but I'll talk. This is isotopes, so we have oxygen and hydrogen isotopes, and we can use these 2 different sources that I just talked about to identify how much of that alluvial aquifer water is from the urban system and how much of it is from the regional system. So this is the average isotope of the water that's coming out of the mountains, so that regional water, that mountain block recharge. And this is the average isotope of precipitation at the University of Utah campus, so that urban water end number. And then all of these are those groundwater springs. So a whole bunch of different springs we measured at different times of the year. We can see they all fall in the middle. And so if we can use this equation to then see how much of the water from those springs is urban water versus how much of it is from the mountain system. And we find that springs that are closer, further upstream have less urban water than streams that are further downstream. But overall, we have somewhere between 13 and 23% of the water in that alluvial aquifer appears to be from urban runoff. So our next step was if we can use what we measure from the urban water runoff to explain that alluvial aquifer chemistry. So we know about 82% of the groundwater is coming from the mountains, and about 18% of it is coming from urban runoff. It's mixing in this urban alluvial aquifer and then coming out in the springs. So we can measure the chemistry of this water from the mountains, and we can measure the chemistry from these springs. Can we then predict what this urban chemistry is and compare it to measurements we're making of that urban chemistry? So I'm going to use two examples, chloride and nitrate. So chloride coming out of the mountains is 13 milligrams per liter. Chloride coming out of these springs is 127 milligrams per liter. And these are average values of a lot of measurements. Nitrate coming out of the mountains is about 0.04 milligrams per liter, and coming out of these springs is 2.1. So I can then use that and those 82 and 18% to predict what the urban water feeding into the aquifer is. So I'm going to predict that the urban water coming into the aquifer is 662 milligrams per liter of chloride and 11 milligrams per liter of nitrate, which is a lot of nitrate. We then measured a whole lot of urban runoff water, and if you're interested in this data, Mallory Millington will have a poster on it this afternoon with a lot more details of all these urban runoff data. But just as a quick snapshot with these two variables, pavement measurements we've done of pavement, so this is water in streets and parking lots, has ranged from 2 to 172 milligrams per liter of chloride, none of which is as high as this prediction I've made of the urban water coming in. But when I then go to storm culverts going into the stream, I see chloride concentrations from around 4 to a little over 3,000. 3,000 was measured during a winter storm when we have road salt actively on the streets that's being brought into the storm culvert. So we do see chloride values that would indicate that our average is possible. That sort of average that we're predicting is within the range of the values we're measuring that are entering this system. We then go to nitrate. I'm predicting 11 milligrams per liter concentration going in, yet pavement tops out at 1.3, storm culverts top out at 2.3, and those are the highest measurements we have. So we don't see any measurements of runoff that are nearly as high as it would have to be for that nitrate value to come out. We also know nitrate is a nutrient. It's not conservative. So nitrate that enters that system is probably going to be used up in the subsurface before it comes out. So odds are what's going in is even higher than this predicted of 11. This tells us is there could very well be a source of nitrate underneath the surface that we're just not measuring. It could be fertilizer. There's some indication from the N15 isotopes of that nitrate that it's somehow some sort of waste product. It could very well just be leaky sewer lines from a really old neighborhood. It could be just from the soil itself. As the water infiltrates into the soil, it's picking up nitrate. So we're not sure, but there is some other subsurface source of nitrate that's adding to this alluvial aquifer. But overall what we found is we have sort of a new proposed model to think about when we're thinking about how to do resource management in an urban environment, and we need to take that subsurface into account. So we have regional water coming from the mountains, we have storm culverts that are feeding stormwater into these rivers, but that stormwater is almost immediately feeding into the subsurface. And we additionally have runoff from all these different surfaces that can both infiltrate in through the ground and come in through these drains, and then further down the subsurface water is coming back into the rivers. And so we need to think about the role of that subsurface when we think about how we make management decisions of our rivers from a water quality perspective. One thing to think about is timescales. So water in Red Butte on the surface isn't going to stay in the river very long. It comes down pretty quickly, but residence time underneath the ground can be multiple years or even longer. So the storm that happens this week, we could still see chloride impacts from it several years later coming in back into the stream. So we have to think about the time scale of any infrastructure changes we make might take longer to see a result. We also need to think about mitigation efforts, and if we're going to use mitigation efforts, they need to account for that groundwater input. One possibility is growing more vegetation along the riparian zone, and that vegetation could intercept some of that groundwater as it's coming in and use up some of those nitrates. So various other things we can think about. I don't have time to present any of the other data here, but we've done some similar work like this in the Logan River to see if this same thing happens at a larger scale. We're seeing the same thing in Logan, where the urban impacts don't show up until several kilometers downstream of where it enters the city. We've also done a little bit of work in Emigration Canyon too, and we're seeing some similar patterns. So this does seem to be a consistent thing happening across the Wasatch Front. On that note, I think I have a couple minutes for questions. So, yes.
Salt Lake City found a golf course infiltration of nitrate in the mouth of the Cottonwood Canyon was a major contributor to groundwater.
Yeah.
Nitrate.
Cool.
Could not all of those lawns
Yeah.
be the source of all of this nitrate going into the shallow?
Yeah, it's very possible.
Including the University of Utah sod.
Yeah, it's very possible that it's fertilizer from the university, from the neighborhood. We don't know yet where it's all coming from, but that's one very likely source.
So you mentioned that it was nitrate was more waste indicative than fertilizer?
Yeah, there's been some, Stephen Hall did some work on the nitrogen-15 isotopes, and those indicate that at least some of the nitrate seems to be from, so the nitrogen-15 isotopes are going to be different coming from fertilizers, coming from waste products like animal or human waste. And I haven't dug into that data fully because it's not my project, but it does indicate that a lot of that nitrate is coming from waste products. But waste products can also be used as fertilizer, so yeah.
Is that consistent with the Logan River and
yeah, we start to see nitrate coming up in the Logan. The problem is where we start to see urban impacts coming in the Logan is also an area where it was tile drain agriculture not too long in the past, and where we start seeing agriculture things, so that gets a little, and the Logan hydrology, because it has all these other canals and things coming in, it's a little bit more complicated, so we're still trying to dig into what's going on there. But yeah, it is. Uh-huh. Yeah. Mm-hmm. Yeah. Yep. Yeah, it's right after that flashy spot, it's a hugely losing reach. So like Miller Park, for instance, is really losing. And I think that's what it is I think and we do see, like during storms, I mean, you see there are times where Miller Park has, you know, tons, like I've seen people pictures of people whitewater kayaking in Miller Park. So it does happen that you do get some flashiness, but we're purposely only measuring during base flow. We're trying to see what the impacts are not during storms. And during that base flow, it is that way. It is kind of interesting, but I think it's the nature of that just really losing system.
I was wondering if there were any like old septic systems in the neighborhood or like that.
Yeah, I don't know, I wouldn't be surprised, but the neighborhood itself is pretty old, and old neighborhoods almost always have sewer pipes that have leaks in them. It's just the nature of human infrastructure. I wouldn't be surprised if there had been some septic somewhere in the past. I just personally don't know. So.
Okay, cool. Big
Thank
round
you.
of applause for Rachel. Thank you.